Okay, hello YouTube. We are recording. I just want to remind you today. So today, your reading for today is 7.6 and 7.7, and for Monday it's 8.1. And I think, but I kind of get the impression that maybe a number of people are. So I think I think this actually sort of a failing of the course sometimes is that we've let the homework trail behind the lecture to sort of a significant extent. And so especially if you find yourself just sort of just like, oh my God, what is going on? What is he even talking about? You really have to sort of, I think we are at a sort of point where you really have to have engaged in some of the homework in order to be following what's going on. So it's okay. We're all behind. I'm like way behind. I haven't graded from problem set 5. My bad. I will. That's my next project, is to get caught up on grading your homework, and pretty soon. Anyway, but in any case, we will sort of forge on. We will have because I think that's. I guess I still think that's probably the best use of our time. There will be a problem session on Friday on PS08 or or wherever you are, whatever you're working on. If you're now a bit behind, that's okay. So we will have a problem session at the usual time at 10:30 noon, handled by Zoom. So please drop by. Even if you just come by and want to say hi and catch up and get caught up, that would be great. Anyway, so again, tentatively, we'll have exam 2 on 2 weeks from today. It'll be done on paper and submitted by Canvas and proctored by Zoom. And the last 5 minutes of today's class will be a rehearsal. Actually, let me magnify it. Let me blow that up. So the last 5 minutes of class today will be a rehearsal for Zoom proctoring. And so basically I'm going to do is I'm going to sort of show you what you have to do in order to sort of comply, to sort of go along with the Zoom proctoring scheme. And I'll show you by doing it myself. And that will be, and just so you know, just to be clear, that'll all be done off camera. I'll turn the recording off, and then we'll do our little rehearsal of the Zoom proctoring, and you can sort of see how that works. Okay, so yeah, so don't worry. No, I'm never going to take a recording of your surroundings. That would be well, that's for the other proctoring systems. Okay, so are there any questions? Does anybody want to say on the chat? If you have any other questions about sort of what is to be done, what sort of work needs to be done, what's happening on Friday, what's due on Monday? Oh yeah, and oh gosh, I guess I should also say again, our deadlines are elastic as even more so than before, but it's also true that outline for PS08 is due tomorrow, let's say. And I'm not entirely even sure I created I'll have to go create the Canvas Dropbox for that. But yeah, but we're gonna have the outline for problem set 8 due tomorrow. Okay, so yeah. Oh, and so are there any questions about what work needs to be done, and sort of our rehearsal, and what's going to happen in our rehearsal in the last 5 minutes of class, which will start at, I guess, 11:40, about an hour, a little more than an hour from now. So can everybody just type yes into the chat to continue? Okay, so at the very least, I don't think anybody has any questions. So let's pick up where we left off. Okay, yeah. So last time we were talking about abstract stuff, but it turns out to be, as we'll see, turns out to be surprisingly important and practical, and like money making of all things. So let R and it is also, I mean, to be totally honest, it is like these ideas are among the fundamental ideas of abstract algebra, and so I can't resist sort of including them. Anyway, so let R and capital R and capital R prime be rings to say that a function phi from big R to big R prime. So the domain is, so the inputs are the domain are elements of big R, and the output is elements at big R prime. Is to say that that function is a homomorphism means that for all little r and little s in big R, phi of r plus s is equal to phi of r plus phi of s, and phi of r times s is equal to phi of r times phi of s. In other words, i.e., phi preserves addition and multiplication. Sends additions to additions and multiplications to multiplications. So that's what a homomorphism is. An isomorphism is a homomorphism that is bijective, that is one-to-one and onto. So to say that two rings, big R and big R prime, are isomorphic means that there exists some isomorphism phi from big R to big R prime. In other words, there's some way to sort of think of this as renaming. So when you have an isomorphism, you want to think of this as being a renaming function. I think last time I had this example of renaming the elements 0, 1, and 2 of Z mod 3. If you name them Mo, Larry, and Curly, and you otherwise preserve the same addition table and multiplication table, then what happens is that isomorphic functions are abstractly the same ring with different names of elements. Okay, so that's what we there were a number of examples that we talked about last time, and examples, of course, are always tougher or sort of more interesting and more substantive. But it just at least at this sort of overview level, this 30,000-foot level, are there any questions about what we talked about last time? So any questions? So type in the chat either good to go on, or yes, or if you have a question. Well, at least nobody has questions, I think. So let's see, where are we here? Oh yeah, and so and let me remind you also that the very last thing we did, the end of last time, we talked about examples of how to show rings are not isomorphic. To show that they are just substantively algebraically different. Okay, so and if you and I guess if you want to see how that works, you can go back and look at the previous slides, or which are posted online, or you can go back and look at the previous videos. Okay, so I guess so let's go on to the last bit of our morphism chapter, automorphisms. Right. I guess I think it's helpful to remember the sort of etymology of this. Homo is a prefix that has to do with things that are similar or alike. Iso sort of means the same, and auto means self, right? So those are sort of that's the reason for that's the etymology of the prefixes on all these different kinds of morphisms, all these different kinds of maps. Yeah. So I think last time Nat asked a very good question, like what's the difference between a homomorphism and an isomorphism? And that the main difference is that a homomorphism can swish lots of different things down onto one thing, and so that means that the two rings are similar. Whereas for an isomorphism, they're actually exactly the same. Hang on, I got a little noise in the background, so let me actually let me ask you on the chat. Can you guys hear my daughter doing her Chinese in the background there? Is it distracting, or is it like just okay? It's fine. Okay, so I'll speak louder too. Yeah, I'm in the same situation as you guys, so we'll just keep going. Okay, so yeah, so for those of you who are working in not the quietest situations, I feel your pain, my friends. Okay, so And automorphism. Okay, so let's talk about automorphism. So automorphism. So the prefix auto means self, and and what happens is that an automorphism is an isomorphism phi from R to R, from a ring to itself. And here is there is actually one example of an automorphism, a ring automorphism, or actually a field automorphism, with which you are familiar, which is this is called complex conjugation. Even if you're not familiar with this by name, I'm sure you've seen this referred to at least in terms of what it does. And actually, we'll get to that in a minute. So complex conjugation. So if R is the ring of complex numbers, it's C. So we define phi from C to C by phi of A plus BI equals A minus BI. And so this is, in fact, usually this is written as follows. So this is written as bar. So if you may have seen this written as the instead of written as in this sort of function notation, phi of A plus BI is A minus BI. It's usually written as the bar notation for complex conjugation. So what this example is all about, it says that so phi is homomorphism. So for homomorphisms, that means what does it mean for phi to be homomorphism? That means that if you take the bar, okay, so what this is really saying is that phi of a complex number z is z bar. And so the homomorphism properties say that the bar of the sum is the sum of the bars, that z plus w quantity bar is equal to z bar plus w bar. And z times w bar is equal to the zw quantity bar is equal to z bar times w bar. And you can check these. So that's what it means for complex conjugation to be a homomorphism. Oh, I should actually put that. That should actually be one of the exercises in the book. That would actually be a good one. And or maybe, unless I did it myself already. And phi inverse is and phi inverse is equal to phi. That is. So what I mean by that, if I take bar z bar bar, I get z back, and so I can undo the effect of complex conjugation by conjugating again. You know, phi of phi of z equals z, or z bar bar equals z. So phi is an isomorphism, yes, because any invertible function is a bijection. And so a homomorphism that is also bijection is an isomorphism by definition, and is therefore an automorphism just because the auto part comes from having the same domain and codomain. Yeah, what I really, I don't know if this deserves like an entire extra page, but let me, because now that I know how to stick pages in the middle of things, I might as well do that. So what you really want to think, so whenever the message is whenever, that was what I wanted to do. There we go. So when we see some field automorphisms in chapter 8, when constructing better codes, it may help think of them as complicated versions of complex conjugation, making the bar complex number. I guess I'll take a little chat survey here. 21 people here, good. So my chat survey is, so how many of you remember seeing complex conjugation somewhere? Like, and like it would probably be when you first saw complex numbers, like when you talk about finding complex solutions or imaginary solutions to quadratic equations. Anybody remember this? Oh yeah, certainly if you took Math 138, you saw you saw complex conjugation. Yeah. So if you don't remember this, I think probably the place where I think everyone is most likely to have seen what happened there? Complex conjugation. Oops. Uh, is that we're going to see in a minute that if you have a real polynomial with a complex root, then sort of if f of alpha is equal to is equal to 0, then f of alpha bar is also equal to 0. Yeah, actually, let me remind you. So maybe, oops, undo. Well, if you only had undo on the whiteboard, huh? You may have seen this as complex roots, a real polynomial in pairs. And the pairs are exactly the complex conjugates of complex conjugates of each other. So so yeah, if you don't remember, well, that's okay. I mean, you're hearing about complex conjugation now, and so the idea. So I'll sort of remind you of how that works in a minute, or tell you about how that works in a minute. And the idea is that other field automorphisms are kind of like that. They're sort of like taking the bar of a complex number, but maybe in a more complicated way. Okay, so right. So what I want to talk about. The last thing I want to talk about from this section, from section 7.5, is what's called what I call the induced automorphism on polynomials. Oh, complicated. So, yeah, just let me say what this really means. I.e., what happens when you apply the an automorphism to the coefficients of a polynomial and leave the x's alone. So I have some. Yeah. So this turns out to be probably one of the more important. Yeah. So all this, there's a bunch of abstract stuff here. I have to be precise, but the idea is that we have an auto. So here's the idea. So let R be a ring, and suppose phi is an automorphism of R. It's a bijection from R to itself that preserves plus and times, kind of like complex conjugation. And I'm going to define. I'm going to try to extend that map little phi to big phi. Oh yeah. So this is not the world's best big phi. So this thing here is maybe more common. It looks like. Is anybody familiar with Green Lantern? It looks like the Green Lantern symbol. So this is the Green Lantern symbol. Okay, maybe not everybody's a comic book geek like me, but the Green Lantern symbol is the capital is the capital letter version of phi. Yeah, Green Lantern. Okay, do people know Green Lantern? Yeah, so the Green Lantern symbol is a capital phi, and then, so this is a.
Well, Master Friends is a total nerd.
Go ahead.
Oh.
Go ahead.
Sorry, my thing was unmuted.
It's okay to say I'm a big. Come on, I'm a math professor. It's okay to say I'm a big nerd. Yeah, so this is a slightly more modest version of the Green Lantern symbol, leaving off the fancy stuff on the top and the bottom. But okay, so that's supposed to be the capital phi from big R bracket x from polynomials to polynomials, coefficients in R, by saying that but this is a sort of precise and formal way of saying that we are applying phi to the coefficients of f. Apply phi to the coefficients f. And if you look, that's exactly what we're happening here. Oh yeah, like it says here, in other words, we get this output by applying phi to the coefficients of f. So it turns out that big capital Phi is also an automorphism of polynomials with coefficients in R, and we call this the automorphism of R bracket x induced by phi. So in other words, what do I mean by induced? No, okay, I'll just start typing. I.e., coefficients, an automorphism of the coefficients of the coefficient ring induces an automorphism on the polynomial ring. So that's what's meant by an induced automorphism. Okay, and so here, the reason that I'm introducing this slightly complicated idea is actually just for this one result. This is what we need. So let R be a ring, and let phi be an automorphism of R, and let capital Phi be the corresponding induced automorphism on polynomials. Then if I have a polynomial with coefficients in big R, and alpha is an element of big R, if f of alpha is 0, then phi of f of phi of alpha is equal to 0. All right, so in other words, an induced automorphism sends roots to roots. So here is the example with which you may be familiar. If you've heard about, okay, so I'm sure you've never heard about in automorphisms and induced automorphisms, and what the heck is he even talking about? But you may have heard of the next thing. So suppose that that f is a polynomial with real coefficients, and so here I want to be clear about what's happening. Here we're applying the theorem. Okay, this theorem, and the proof is not that important, so you can read about it in the text if you want to, but if you want to just sort of accept that, that's fine too. And here we're going to take the ring of coefficients R to be the complex numbers. Complex numbers. And our little phi is going to be complex conjugation, which we've been discussing before. And so if we take, oh, I think I'm going to need another page here. So if we take in this case, if we start off with this polynomial with real coefficients, and we have a complex root of f of x, and so our starting point is that f of alpha equals 0. So that's what's meant by saying that alpha is a complex root of f of x. So we're going to start with that fact that f of alpha equals 0, and we're going to apply the theorem. So like I said, I'm not so concerned whether you about the proof of this theorem, but I do want you to try to understand what the theorem says, what the meaning of the theorem says. So this says that if f of alpha equals 0, okay, so that's what we're starting off with. Suppose alpha is a complex root of f of x, then phi of f applied to phi of alpha equals 0. So what is capital Phi of f? So capital Phi of f is exactly f applying the bar, the complex conjugate bar, to the coefficients. But what happens here now is that the coefficients of f are all real. We start out by saying that coefficients of f are real, so they're not changed by taking complex conjugates. So capital Phi of f is the same. It's just the same polynomial as f. Yeah, so capital phi of f is just f again. But now the theorem says that let me switch to pen here. Alpha bar phi applied to alpha is a root of phi of f, which is just f. In other words, since f is a polynomial with real coefficients, we have that f, switching back to pen, f of alpha bar equals 0 as well. So if you've heard of this, the way this in slogan form, undo. In slogan form, you may have vaguely heard the roots of a polynomial with real coefficients, or the complex roots of polynomial with real coefficients come in conjugate pairs. And the pairs look like alpha and alpha bar. In other words, they look. One of them will look like a plus bi, and the other one will look like a minus bi. Anyway, just curious. Does that sound vague? Well, I'll just take it. It's okay if you say no. Does that sound vague, like maybe something you maybe heard before? Couple yeses. Yeah. Anyway, this is okay. So this is. Oh yeah, right. Definitely. If anybody took, so Ishan mentions in Math 123, but if anybody took any kind of differential equations class, that actually is an important part of any kind of differential equations class, because that's how you that's how you end up getting sines and cosines, sines and cosine solutions to some very common differential equations. Yeah. So this result up here is just a very fancy way of saying the same thing. That if you have it's a fancy generalization of the same thing. That if you just as a polynomial with real coefficients, its roots come in complex conjugate pairs. If you have in general, if you have what happens, the way we'll actually use this is that if you have a polynomial whose coefficients don't change upon applying an automorphism, then so we'll use the following generalization. This generalization, if the coefficients of a polynomial f of x don't change when applying an automorphism phi, then the roots of f come in what are called in phi orbits, which is something we'll define later, but they kind of look like as follows. They'll look like alpha, and then phi of alpha, and then phi of alpha. I mean, you just take alpha and you just keep applying phi to it. And so for complex conjugations, that stops here. You sort of circle back to alpha. But for a general automorphism phi, you can sort of apply, you can end up applying phi lots and lots of times, and keep getting something new. I know it's very hard to believe that this is somehow going to make you money, these orbits, but well, you'll see. You'll see in about 2 weeks. I think. Yeah, I guess maybe sort of just before, or yeah, next week you'll start to see how this works. All right. Right. Any questions? Any questions so far, or should we? Oh, question. Is it infinite? Ryusei asks, is it infinite? By it, do you mean the orbit? Yes. Okay. So yeah. So this process. Let me put this in a different. That excellent question, Ryusei. So does this process go on forever? And the answer is, in our case, we, as we'll see, we mostly use finite rings. Well, in chapter 8, we'll only use finite rings with finitely many elements. So this must circle back eventually. So in general, this can go on forever. But in our case, in chapter 8, this will only the rings that we use will only have finitely many things in them, and so eventually we'll have to go. You end up going back to alpha. So you say, does that answer your question? Okay, thanks. All right. Yeah, good question. Okay, so any other questions before we go on to probably before we finally get to probably one of the most money-making things that's in the entire course, which is finite fields. Any quick questions before we get on? Go make some money. Okay, let's go make some money. Yeah. All right, so finite fields. So, well, okay, so before we can make some money, there of course have to be definitions, because this is an algebra class after all. So, definition. The order of a field F is defined to be the number of elements in F, and therefore a finite field is defined to be the same as a field with finitely many elements. And so the example of a finite field that we have seen, example of a finite field, is FP, which is really for us so far is just the ring Z mod P. So though I guess I should say where P is prime. So that's the main example of a finite field that we have seen, oh geez, I didn't even ask sort of what the sort of motivating question is here. So let me put that. That's so interesting that I'm gonna debut a new color here. I'm gonna use this sickly olive question. What are all possible finite fields? Fields like, and a sort of deeper question. I mean, well, maybe not. Well, yeah, a deeper question, and it's certainly a more profitable question is how do we compute? That's worth. Question: how do we do computations in a finite field? That is, I mean, you sort of have to know the answer to question one. Question one before you can answer question two. But you will be okay. You are correct in thinking that maybe question two is that's actually the money making one. So yeah, how do we do computations in a finite field? So so before that, but like I said before that, we need to have a bunch of different definitions. So let capital R be a ring. Since capital R in our class, our capital R is a multiplicative identity called 1. for positive integer n, we can abbreviate n times 1 to be 1 added to itself n times. So that's just an abbreviation. So we're going to. So the thing we're actually defining is the characteristic of R. So the point of this definition is to define the characteristic of R. So this is the important thing. So we want to define the characters. We define the characteristic of R as follows. So if the characteristic of R is defined by taking the following process. You add 1 to itself over and over repeatedly and see what happens. So yeah, so the idea is that you take 1 to itself. I mean, at least, so if you have some way of computing inside this ring, you take the number 1 and you add 1 to itself over and over again and you see what happens. So it could be that eventually, if you keep adding 1 to itself for some positive integer n, then the characteristic of R is the smallest possible n that gives you 0. That when you add 1 to itself many, many times, you get 0. So so the first time that happens, that's the characteristic of R. So that's one case. On the other hand, it's possible that it's actually sort of kind of like the question Ryusei was asking about here. If you keep over here, if you keep doing this, does it go on forever, or does it stop? So it could be that in some fields that if you add 1 to itself, if you keep adding 1 to itself, you never get 0. So for example, if you have the integers, I guess I should have an example for this, huh? So if you have the integers, the ordinary integers, and you keep adding 1 to itself inside the integers, well, you know very well that if you keep adding 1 to itself, you're never going to get 0. So by convention, there's these standards. This is not obvious that this, you might sort of think like, well, maybe the characteristic of the integers of R should be infinity. Well, there's actually good reasons for that to be true. But that's not the convention. That's not what everybody else did. So, and we have at this point no choice, because people have been doing this for a century, and they call that characteristic 0. So okay, so there's some reason to call it characteristic 0. Anyway, so the point is, if you keep adding 1 to itself and you never get 0, then we say the characteristic of your ring is 0. So and the two examples that you want to keep in mind, here are the two examples that you want to keep in mind. Is if you have z mod m, the characteristic of R is m. That makes sense, right? If you're working mod 10, well, if you keep adding 1 to itself, the first time you get 0 is when you add 1 to itself 10 times, because you get 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 10. 10 is equal to 0, and that's your characteristic is 10. But it's also true that if you have if you take polynomials with coefficients in the actually, it occurs to me I can stick in one more useful example here. So, oops. Yeah, there we go. Yeah, occasionally, like, my screen freaks out and does that psychedelic thing. Sorry, you might have noticed. So yeah, but it's also true that the characteristic of the ring of polynomials with coefficients in mod p, is actually just till p. It's not somehow different or bigger, because we always have 2 equal. So for example, we always have 2 equals 0 in f2 bracket x. So for example, example, if f of x is a polynomial in f2 bracket x, then and if you look at f of x plus f of x, that looks like something like I don't know. Okay, now let me switch back to pen. It's going to look like something like a n x to the n, oops, x to the n plus yada yada up through a 0. So that's f plus a n x to the n plus da 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 up through a 0, which is equal to, well, what you have here is you get 2 a n x to the n that was not such a great n. X to the n summed up through 2a0. But remember, it's still the case that all the coefficients are taking mod 2, and so we just end up with 0 x to the n summed up through 0, which is equal to oops, whoa, what was that? Sorry, old man is old. Okay, dang it. There, okay, equals 0. So so if you look at the sort of overall message of what's going on here, characteristic 2. The point is that the characteristic of a ring being 2 means that 2 equals 0. It's still true that 2 equals 0, even though we have a lot more elements in the ring than we have in Zmod. Even though the ring has a lot more stuff in it than just Zmod 2, it's still the fact that the characteristic of this ring being 2 is equal to 2 means that it's still true that 2 equals 0, even though there's a lot of other stuff in it, a lot more extra stuff in it. All right, so that's I think that maybe sort of gives a good idea of what characteristic 2 means, and characteristic 3 and 7 and whatever are actually kind of similar. So are there any questions about what characteristic 2 means, and therefore probably what characteristic m means? Okay, so now so that's sort of what it kind of means an example, but I do want to also go back and emphasize the definition. The characteristic of a ring is the number of times that you need to add 1 to itself in order to get 0. Okay, so now let's talk about the characteristic of a finite field. So theorem: let f be a finite field, then the characteristic of f is equal to p for some prime integer p. So proof. So I want to discuss why this is true. So the point. So let me actually say the motivation for this, like the meaning of this theorem. As we'll see, so every finite field is based on z mod p, on fp for some prime p. So it's not obvious that's what this means, but that turns out to be what this means. Okay, so let's prove that, because it's sort of I think it's useful to go to look at this proof, which isn't too long, in order to understand what characteristic means. Okay, so it is possible that is it possible to have characteristic 0? Because remember, that was one of the cases. In that case, we would have that 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1, etc., are all different elements. So f would have to contain infinitely many different elements. Not possible because f is finite, has finitely many different elements. So no, you can't have the characteristic of f be 0. Is it possible? Is it, on the other hand, maybe it's possible that the characteristic of f is composite, is equal to the product of 2 integers, each of which is greater than 1. Well, what would happen in that case? In that case, we would have a times 1 times b times 1 equal to AB times 1. And remember, to say that the characteristic of F is equal to A times B means precisely that AB times 1 is equal to 0. But on the other hand, we would have A times 1 and B times 1 not equal to 0. That would mean, oh boy, here's a vocabulary review. It's been a while, so if you, I understand if you don't get this, but I'm going to try to do one of my shout out quizzes by chat. So that would mean that F would contain. So does anyone remember the name of things and elements of a ring? Does anyone remember the name of elements in the ring that where you have or the phenomenon where you have two non-zero things in a ring that multiply to get 0? Those are called, on the count of 3, 1, 2, 3. Go ahead and type it in the chat. Yeah, that's right. Good. Zero divisors. Takes you back, huh? Would contain zero divisors. So 0 divisors, which can't happen in a field. Yeah, that was a while ago, huh? Right. So yeah. So in particular, these two elements here would be our 0 divisors. Yeah, two non-zero things whose product is 0, and so we can't have characteristic F equals 0, and we can't have the characteristic of F be non-prime, and so we're done. Yeah, so it's not a big deal, but it is true that but that does mean that any finite field has prime characteristic, has characteristic P for P prime, which means that any finite field has some copy of the integers mod P, because yes, it's a copy of FP because FP is really just the integers mod P sitting inside it. And so what happens is, so remember, one of our fundamental problems here, what is this section trying to solve? What do all possible finite fields look like? How do we construct a sort of arbitrary finite, all possible finite fields? So the starting point is that any finite field has to have some copy of the integers mod P sitting inside it. And so what we're going to do to build any particular example of a finite field, or sort of all possible examples of finite fields, is start with that copy of Z mod P of FP, and then sort of build on top of that. Okay, again, any questions so far? Okay, so, excuse me, oh my goodness, it's getting close to it. Can you hear my, that sounded really loud to me sitting here in this room. Could you hear my stomach rumbling just now? Thank you, Kyle, for saying no, even if it's true, especially if it's true. All right, I guess I'll find out on YouTube later on. Okay, so the multiplicative. So now we know that every finite field has a little copy of Z mod P sitting inside it for some P. So now let F be a field. So we use F times to denote the set of all non-zero elements of F, all of which are units because F is a field. So remember, the definition of a field is that a field is a ring in which every non-zero element is a unit. So a non-zero ring in which every non-zero element is a unit, and so we call that we call F times the multiplicative group of F. And now, so some of you, well, actually, oddly enough, probably the people who would object are the people who actually have heard of this term group. So because if you haven't heard of the term group before, you're probably just like, well, why is he calling it a group? Why not a set or I don't know. So group. So I just want to be fair, I want to mention that we will later to define the term group, but for now, group is not defined yet, not yet defined. You could just say set if you like. But, you can just think, or I want you to say the word group, but you could think group when you see set when you see that. And so for now, group is just another strange word for set. We'll see later it's a particular kind of set. Okay, so that's the multiplicative group is just the non-zero of a field. It's just the non-zero elements of that field. Okay, so here's another definition. So let f times be the multiplicative group of the field f, and suppose that we have some particular non-zero element alpha. Alpha is an element of f times. We define the cyclic subgroup generated by alpha again. This is so again not defined yet. So yeah, so again, the word subgroup is not yet defined, but it will be later. Yeah, this is just kind of like we work with rings for quite some time before we actually define what a ring was. So here we're going to do some stuff with groups before we get an idea what a group is. By the way, so let's see. So let me just check just to see. Oops, that's not where I meant the scrolling to happen. Has everybody? So I think those of you taking 146, you guys have gotten the groups already. Those of you taking crypto. Yeah. So so those of you who happen to be taking crypto right now have seen this idea already. So and this is actually I think this more or less the same context. Anyway, but if you haven't, that's okay. We'll spend just a very little time developing the very small amount of group theory that we need later on. All right, so anyways, we define, so if alpha is an element of the multiplicative group, we define the cyclic subgroup generated by alpha to be the set bracket alpha, which is the set of all powers of alpha, positive, negative, or zero. So I guess let me it's better if I sort of illustrate this. So the idea is that the cyclic subgroup generated by alpha looks kind of like, well, it has alpha to the 0, which is 1 in it, and it also has alpha, and has alpha squared, and yada yada. But it also has alpha inverse in it, and alpha to the -2, and so on. All right, so that's what the cyclic subgroup generated by alpha looks like. But remember, actually, sort of relevant to, if I may repeat, Ryusei's excellent question from about 10 minutes ago. I should mention that if capital F itself is itself finite, then only finitely many of these things can be different. And so so even though I kind of made this look like an infinite set because it goes on forever, this might just sort of end up repeating itself quite a bit, and so it might actually be a finite set in disguise. Anyway, so yeah, so the cyclic subgroup generated by alpha is the set of all all integer powers of alpha, positive, negative, or 0. Okay, finally, so let f times be the multiplicative group of the field f, and suppose alpha is an f times. To say that f times is cyclic means that there exists some fixed alpha. Oops, this is a typo. So this should not be here. My bad. All right, so let me start again. So let f times be the multiplicative group of the field f. Period. To say that f times is cyclic means that there exists some particular alpha in f times, such that f times is equal to the cyclic subgroup generated by alpha. Or in other words, this means that every element of f times is some power of alpha. And so if f times, and this, I hope this next word sounds vaguely familiar from the distant past, from those, it seems like 10 bazillion years ago, like an ice age ago, like an ice age of ice ages ago, back before quarantine. Oh my God, was there even such a time? So if f times is actually equal to is actually equal to the cyclic subgroup generated by alpha. We say that alpha is a primitive element of F. So, and remember, we did that before. So it is a fact. So, so this is a fact. Will we to be not to be let's say proof will be is beyond our course, is beyond the scope of our course. It's not much beyond the scope of our course, but it is a little bit beyond the scope of our course. So I think for us, I'm just going to ask you to take my word for it. So it is a fact that every finite field has a primitive element. In other words, if F is a finite field, then its multiplicative group F times is cyclic. In other words, every finite field must contain a primitive element. And so we saw this before in practice. Remember, we had all this back when we first introduced modular mod P or mod M more generally. Back when we first introduced the Z mod M, we saw that, at least in the first few examples, if you look for long enough, if you look for hard enough in Z mod P, you will run into a primitive element. You'll run into some element whose powers, and remember, this is to repeat myself again, what's a primitive element? I.e., an element whose powers eventually hit every non-zero element of F mod P, FP. So, so you may vaguely remember. I think we had like one homework problem about that. And in fact, if you sort of keep looking around, you'll run into lots of them. But I think the homework is just like, is 2 a primitive element? Is 3? Try it and see. But yeah, in practice, we saw that eventually, if you root around long enough, you'll hit a primitive element. Okay, so now, what this theorem says, which is it's kind of an amazing fact, but even if we're not going to prove it or really discuss the proof in this course, it's an amazing fact that the multiplicative group of any finite field is cyclic, and so so no matter what your finite field is, and we'll look at some kind of wacky ones, and I think probably starting on Monday, there's going to be a primitive element in there somewhere. Amazing. Okay, so now, actually, I think this is sort of worth looking at in full before I. Whoops. This next bit is worth looking at in full before we dig into the details. Odors. They're nothing like. He said odor. So this is a typo, obviously. So I want to sort of look at the full view of this. So I want to talk about orders of primitive elements. So if you can sort of look at this whole page, this defines what the order of a primitive element is, and states some facts, which again we'll prove later. So what is the order of a primitive element? Okay, so let F times be the multiplicative group of the field F, and so as alpha is an element of F times. Well, if alpha to the n is equal to 1 for some positive integer n, so if that's possible, if it's possible to take a power of alpha and get 1, then we define the order of alpha to be the smallest possible n, such that alpha to the n is 1. The smallest possible positive n, I should say. Oops, typo again. Let's see if I can actually fit that in here. It's the smallest possible positive n. Oops. And I can't quite get that in there. Oh well. It's the smallest possible positive n anyway. So it's that alpha to the n is equal to 1. So it's the first. It's the power that the first time gets you back to 1. Otherwise, if it's the case that alpha to the n is never equal to 1 for all positive, this sounds really familiar, right? This is actually very much like, whoa. This is very much like the definition of characteristic, as you can see here. It's sort of like it's the first time you get back to the identity. So the characteristic here is defined by the first time you get back to the identity, and over here, the order of an element. An element of the multiplicative group is also defined by the first time you get back to the multiplicative identity, back to 1. In other words, if that never happens, we say that alpha has infinite order. Okay, so let F be a field of order n, and let F times be the multiplicative group of F, and suppose alpha is an element of the multiplicative group, then 1. The order of alpha is equal to the order of the number of elements, the order of, in other words, the number, i.e., the number of, i.e., the number of elements in alpha, and in the cyclic Hilbert generated by alpha, and it follows that alpha is primitive if and only if its order is equal to n minus 1. So the primitive elements of a finite field are the ones that circle back to 1 only when you take their n minus 1 power. Okay. Oh, so let me actually sort of do this in general. So here, do this in this. So here we have a specific example, F11, which is when n equals 11. And so what condition 1 says is that being a primitive element has order 10. So primitive element has order 10. That's what the theorem says in part 1. Part 2 says if k is the order of alpha, then the order of alpha to the m is equal to k over the GCD of k and m. I think that one we'll have to see that in practice. It's not so easy to state. It's much easier to see in practice than it is by sort of just plugging in and just sort of and just specifying what's going on. I want to fix that 0. Okay, so for part 1 of the theorem is that you can sort of say by specifying. So part 1 of the theorem says that a primitive element is exactly one that has order 10, and theorem part 3. The part 3 of the theorem says that any element has order dividing 10 has order 1, 2, 5, or 10. So so that means the fact that any element has order 1, 2, 5, or 10 means that so if we take powers of an element and we don't get 1 by the 5th power, element must be primitive. Okay, so parts 1 and 3 of this theorem actually give us a slightly shorter way of locating a primitive element mod 11. So let's try the example. So let's consider question: is 2 a primitive element of F11? 3 minutes till I'm actually of F11. For once, I'm actually keeping track of the time. Well, so let's see. So 2 to the 1 is 2. 2 squared is 4. So that means already that because we took 2 squared and we didn't get 1, we see that the order is not 2. Okay, but continue. We got to keep going. 2 cubed is equal to 8. 2 to the 4th is 16, which is 5. Remember, that's 5 because we're working mod 11. And 2 to the 5th, multiply 2 again, we get 10, which is not 1. It's actually minus 1. And so we see, by looking at the first 5 powers of 2, we see that the order of 2 is greater than 5. See, the order of 2 is greater than 5, so it must be 10 by the theorem that we are just stated and haven't proven yet. So 2 is a primitive element of F11. Okay, and it is time for our experiment. So is everybody ready to try this? Okay, so are there any, I guess we have 1 minute, so are there any quick questions about what parts 1 and 3 of this theorem, let me pull back to the whole page view. Are there any questions about what parts 1 and 3 of this theorem say, and sort of how we applied that to sort of make the job of finding a primitive element mod 11 a little bit easier? Make sense? Hey, we got a bunch of people here now. All right, and you can go ahead and keep muting yourself. I hear a little bit in the background. All right, so I'm going to stop the recording now. Bye, YouTube, and I'm going to try to bring up and I'm going to try to simulate. So everybody, turn your camera on, and we're just spending the last 5 minutes trying to say hi to each other.